So we're facing this problem here. We have a sample of calcium fluoride and we want to determine molar solubility. So in other words, how much calcium ion and how much fluoride ion are we going to get out of this sample of what is largely insoluble. So if you're looking at this from the laboratory perspective, you just have a test tube of a salt that mostly is just laying at the bottom of the test tube. But a tiny amount of that is going to break up into ions of calcium and fluoride. And in this case, we're provided with some information that indicates we actually have an existing concentration of calcium nitrate in solution that's going to disrupt this equilibrium slightly. And because of that, we're using an ice chart. And the beauty of our ice chart is that we can keep tabs on what's going on from start to finish with this problem. And then we can evaluate our concentrations at the end. So, sometimes with an ice chart, we call that last entry in here the ending quantities. But, technically it's an equilibrium at the end. So, we throw all of our ingredients into the test tube. We allow this to settle out, and what we end up with, that's what we're trying to calculate, our equilibrium concentrations. So this first entry here, so each species in here gets its own entry in the ice chart, right? So we've got our calcium entry, our fluoride entry, and then our starting compound here, the calcium fluoride. This is easy because it has no entry. Okay? It's not participating in any of this because it's not dissolving in solution. So that's fairly straightforward. Now, the problem tells us, though, that we're actually starting off with 0.003 molar calcium ions. And you can do that just by taking a soluble calcium salt, like calcium nitrate in this case, and dissolving it such that you get this concentration. And so in this case, we're actually starting with that concentration of calcium already in solution. There's no mention of fluoride, so we're assuming we're starting off at 0 here. This is it. This is what we're starting off with. And then the change, as ever, causes us to form a certain quantity of calcium. We don't know what it is, so we'll call it X. And it does that in the ratio of the balanced chemical equation. So we only have one of those, so we don't write ones in front of our X, so we're going to get some quantity X of our calcium. And then for the fluoride, that's going to go up by 2X. And that's because we've got 2 of these, okay? And then at the end of it all, we just sum up our entries in our ice chart. And so for calcium, it's going to be that concentration we started with plus whatever is going to actually dissolve and form a little bit more. And then in the case of our fluoride entry, we're going to end up with some quantity 2x, because we're going to get twice as much just based on that balance equation for this dissolution process. And now we'll see what we can do as far as using these expressions with the KSP, that equilibrium constant, to determine what is that value of x. And that'll be in the next part.